Welcome everyone to IE342 Quality Control, and today inshallah we'll talk about the variables control charts. This is considered to be now the core of the quality control when we start learning about the control charts in depth and see the differences between them, how we develop them, when we use each one of them. This is where we will spend the most of the time. Chapter 6 include 3 types of control charts, all of them under the variable control charts. The variables are continuous data, as we know, like a length, weight, dimensions, and so on. The 3 types of control charts we will cover are the X bar R control chart, XS, and the moving range or the individual control chart. Today we will cover the first type, which is the X bar R. First, we need to know what is the objective of having the process under control. The objective of having process under control means that both the variability are reduced and also the mean is standardized with the specifications. So if we look to this figure, shows the need for the controlling, why we need it. The first one, which is figure A, shows the ideal case, where is the mean of the process is meeting the center line of the specification, as well as the specifications are within the control limits. On figure B, we see that the mu or the mean is shifted from the specified standardized mean. And in this case, we see that the mu is greater than the mu naught. And in the last figure on C, we see how even if the mean is meeting the mu naught, the variation or the variability is too high, and that's why the standard deviation, it is greater than the specified standard deviation, and we see the spread is exceeding the limits. And we will have more parts or more service transactions beyond the specification limits. As you see also the bell shape, it is kind of spreaded and relaxed. As it much gets narrower, as mean that the products or the transactions are meeting the specification. The first type of the variable control charts is the X bar R. This is the most common used. And in this chart, we use the X bar referring to the average of the data measures, the R referring to the range. And the range we calculated based on the subtraction of the max and the minimum. We will see more about the formula here. What I would like to highlight here, and it is very important, the sample size and the frequency of the sample of the control chart X bar R, because this is one of the decision criteria when you decide about to use X bar R or XS, is the sample size and the frequency. If we have the sample size here for up to 6 also, this is a decision criteria, and you have a data is a variable to use X bar R control charts. The number of samples considered to be at least 20 to 25. This is a minimum. As much you can get, as it is better, but also consider that sometimes sampling, it is cost, because it will cost you from your product, it will cost you from the operators, and so on. So you have to design the sampling in a way that meets the requirement, at the same time get you the needed information. What we mean here by X double bar is the average of the average samples. So if we have 20 samples or 25 samples, each sample has 5 readings. The average X bar refer to the average of the 5 readings for some sample 1. X bar 2 is the average readings for the 5 samples of sample number 2, and so on. The X double bar is the average of all the averages of the sample. The same for the R is the R maximum minus the R minimum for every sample, and then we get the R bar, which is the average of the ranges. We will see all that in example. This is a summary of the control limits formulation for the X bar R. To draw X bar R, there are 2 charts drawn at the same time, one for the mean and one for the range, which is monitoring the variability and the specifications. Let's go to see the, what is the formula? Yes, here. Yeah, we will come to this table here. This table is not in the original slides. I added here to show you how we get the values of the constant in the X bar R chart. In the calculation of X bar R control charts, the upper control limits equal to X double bar plus A2 multiplied with R bar. A2 here is a constant. This constant, you get it from a table. This table is designed based on the number of sample or the sample size you have. Let's say an example, we are using a sample size of 5. So N will be equal 5. At this case, A2 will equal 0.58. So you replace the value of A2 to 0.58. R bar and X double bar both are calculated from the data you collected from the samples. Those constants, you get them from the table, which you can have it during your exam or project that you will work on. The process variability monitored using the range, and also the control limits will be drawing the average of the data measured in the X bar chart. In order to calculate the standard deviation, since we don't have the population, we do estimates. This is what we learned in statistics. Standard deviation, when it has this hat here, that means it's an estimate because we have samples. When we have the samples that collected for the control charts, we can calculate the standard deviation by dividing R bar, the range, the mean of the range or the average of the range, divided by D2. Again, all these constants can be found from the table here. So looking for D2, I can give you the extent of this table. It will have the D2. I will upload it on the Edmodo. It will have the D2 value here in other column. So you can have it based on the number of samples. For example, here D3 and D4 for the R chart or the control limits for the R charts can be found from D3 here and D4 columns. Okay. This is how we calculate the control limits as well as the center line for each control chart. So basically, at the end, when you do implement X bar R control chart, you come at the end with 2 plots, one for the X bar and one for the range. So let's take some conditions needed and some instructions needed when we implement X bar R control chart before we go to the example. Those important, and it's very, very, very important. You need to know them and you need to highlight them and read them very well. When you decide about selecting the control chart for the variables, we follow the sample size. And from the sample size, we can say or determine whether X bar R control chart will be used or XS or moving range. If the sample size is between 3 to 5, we use the X bar R control chart. The number of samples should be at the minimum from 20 to 25. Usually 25 is the ideal to be used because it is economical and at the same time give you enough readings. When we have out of control points, the point should be removed and we examine the assignable causes. So we have out of control point. At this case, we should examine for the assignable causes that cause the out of control. If the assignable causes are found, then we discard the points from calculation and revise the control limits. So the first step you do when you find out of control point, you check for what is the reason, maybe a machine failure or something went wrong in the transaction of the system or the software application that you are using to conduct the service, server went down, any of those conditions. After you diagnose the reason, then you remove this out of control and you redraw the control charts again. Continue after that, examine until all points are in control, okay? If no assignable cause is found, that's mean if the process becomes stable and no out of control, you have two options. Either if you would like to investigate when it's in control and it's stabilized, you have two options. Either number two, that's remain everything as is, no changes, and leave it as is, or try to eliminate some points that is very close to the out of control. So eliminate point as it is like assignable causes, and then revise the limits, or leave the process since it is stable and there is no out of control. Those are very important. You have to know them when you deal with the X bar R chart. If there are many out of control points, they should be examined for patterns and the process, identify the process problem. So if we have not only one point out of control, if we have one point, then as we said, we check for the assignable causes, we remove the point, we redraw the control chart again and check the process. But if there are many out of control, then the process has some issues, and this has to be examined carefully because maybe the process is not capable to be conducted and perform as it should be. And that's lead us to an example where we have to check after we draw the control chart, the process capability, whether the process is it capable to perform or is not capable to perform and bring you products or services under the specification you have set. This is an example here, a data set. This is the sample number. That's mean sample 1. And sample 1 has 5 readings. So we call these the number of the sample size. The sample is, the number of samples is 25. The sample size is the number of readings under each sample. We have 5 readings, so the sample size is 5, and the number of samples are 25. Those are the identification numbers that you need to know for every type of control chart. To find the X bar for 1, that's mean X bar for sample number 1, which has those 5 readings, you get the average for those 5 readings, starting from 1 until 5. And you write the average here under X bar 1. The range for sample 1, it will be found from the maximum minus the minimum on the first sample. The first sample maximum is 1.69 and the minimum is 1.32. So the subtraction between 1.69 and 1.32, it will give you the range for sample 1. You will do the same for all the 25 samples. After you calculate those columns, the X bar and R, then you can find the X double bar. X double bar, nothing but the average of all these averages. So you can find it here at the end. It will equal to 1.50. The R bar is also the average of all these ranges for the samples, and it is equal to 0.3. If you found those two, then you are ready to draw or construct the control limits as well as the center line for both control charts, X bar and R chart, following the formula that we have stated earlier. Now we have the X double bar, we have the R bar, A2, D4, and D3 can be found from the tables that given here. So we can find them from the table, and we can calculate the control limits and the center line, as you can see in the slide here. So the upper control limit calculated using R for the R chart, R bar multiplied with the D3. D3 can be found from this table here. We have the sample size is 5, because why? We have 5 readings, 1, 2, 3, 4, 5. Every sample has a size of 5, and the size found it in this table from this column. So we have 5 sample, D3 is equal 0 and D4 equal 2.11. So D3 equals 0 and D4 equal 2.11. When you multiply it with the R, that will give you the upper control limits and the lower control limits. The center line for the R bar chart is already found from the table, from the readings when we calculated the R bar here. This is considered to be the center line, 0.325. 0.325. What about the X double bar control limits? The upper control limits calculated using the X double bar, which found it from the previous readings, A2, which can be found from the table here, A2 for size 5 equal 0.58. And you can see it here is 0.58, which is the same, 0.577. That was just 2 digits rounding. Multiplied with the R bar also found from the readings, and that is the upper control limits, and the lower control limits, the only difference is the minus instead of the plus for the A2 R bar. The center line is the X double bar itself, which is found from the readings here, as we mentioned, 1.50. Then you can draw the control charts for the X bar, which is on the top here, and the R bar chart, which is on the down here. Before we move to the process capability, I will show you now how we can do that on the mini tab. So I will share the screen now, and we start do on the mini tab 2 examples. This is an example on the mini tab to draw the X bar R chart. We have 3 machines, and each machine has a sample, and the sample size are 5, and number of samples are given here, around 20 sample frequency. We need to draw the control chart for every machine. Those are not samples, meaning that machine 1 has its own sample, machine 2 has its own sample, and machine 3 has its own. So we have 3 different control charts. So basically, you can delete those 2, and you can draw the control chart only for machine 1. This is one type of the data readings. You are collecting the readings from different machines or from different resources, okay? And then you code the group. What does the group mean? The group for the sample group ID means that this is for sample number 1, this is for sample number 2, and this is for sample 3, and so on. For every sample, you can see that there is 5 readings. That means the sample size is 5. Then you can go to stat, control charts, and then variable control charts for subgroups. And then the first one is the X bar R. When you click here, you select the data. When I choose here, all observation for a chart are in one column. That means the samples are in one column, as it is in this example. So we will select it from here. Then we select machine 1, machine 2, machine 3, and then when it asks you the subgroup size or the group ID, you select the group ID to identify this is the reading number 1 for sample 1 for each machine. This is the same, the reading number 2 for sample number 1 for machine 1, 2, and 3. So all these 5 readings considered to be sample number 1, okay? And that's the meaning of the coding. So when you have sample size 5 and you have 3 machines, so each machine will have 5 readings. The 5 readings are coded as group number 1 because this is sample number 1. And by doing this, the Minitab will know that in this column, these readings belong to only one machine. Also in column 2, those readings belong to machine 2. So it will be separate from this one, and it will draw the control chart for each one of them. When you press OK, you will have the chart. You see them here in the figure, machine 1, machine 2, and machine 3. When you have the figure, you can press on the tab here, and you can save the graph. If it's asked you in the exam to upload a graph, then you can save it and upload it later. Or also you can print it, or also you can edit on the graph by drawing if you need to, or you can send it to Word or PowerPoint for presentation. If you double press or double click on the figure, it will be enlarged here so you can read it well. Here is the upper control limits, the lower control limits, and the X double bar for machine 1, and the range for or the R chart for machine number 1. We have out of control here in machine number 1, and also in machine number 3, we have out of control events. You see them are crossing the control limits, the upper control limits. And also here, we have another point is exceeding. In this case, we follow the steps that we have mentioned earlier. We have to detect the causes of the assignable or special events and eliminate those points and redraw the control chart. So we identify those points and we eliminate them after we know what is the causes of that event, and then we draw the control chart again. Okay, another type of data readings, as the one was given in the examples of the slides. You have samples, 25 samples. Each sample has a size of 5 readings, but all of them for only one machine, let's say. So imagine if these readings are for machine 1. So all these data are for machine 1. No coding is needed for the sample size. or the subgroup of the samples, because all of them representing the same machine, okay? But we have 5 readings here for every sample, as we had before here. We have 5 readings here. For machine 3, we have 5 readings for machine 2 and 5 readings for machine 1, all of them coded as sample number 1. If we have this type of readings, then what we do, the same control charts, variable control chart for subgroups, X bar R, and then we click. And instead of having all observation for a chart are in one column, we select observation of subgroups are in one row of a column. Why? Because all the readings of the sample size are in one row. This is sample number 1 in one row, row number 1. And all the samples for row number 2 or sample 2 are given in row number 2. Then we select the data from the column X1, X2, X3, X4. So we have for a sample size 4, not 5, I'm sorry, here it is 4, not 5. And no coding is needed because it is reading the data row by row. After you click OK, you will get the control chart for those readings. And again, if we press, we have the X bar or X double bar is 110, the upper control limits, the lower control limits, the same for the R bar chart. No out of control event, but also you can, in this case, if there is no out of control, it asks you 2 things you can do, either to leave it as is, or you can try to eliminate some points like similar to be out of control like this one here, and try to redraw the control chart and check for any observations. Cases also can be done reading the rules that is mentioned earlier in the previous chapter 5 about having 3 out of 4 points or 7 out of or 8 out of 9 points. All the other rules that we have mentioned from Western Electric handbook or reference, or the others for sensitivity analysis to study those control charts. That was the example for the control charts for X bar R. Let's go back to our slides and continue. After we draw the control chart, there is a point needed also for an extra investigation about the data, which is the process capability or estimating the process capability. In order to conduct the process capability, we need to have estimate of the standard deviation, and the estimate of the standard deviation can be found from the formula here that mentioned earlier, R bar divided by D2, and D2, as we said, it is a constant. We can find it from the table. When we get the standard deviation, which is 0.13, in this case, we can calculate the proportion of the products or service transactions that will be beyond the control limits. So they will consider to be non-conforming or defects, as we talked in the Six Sigma previously. How we calculate that? We get the probability or the proportion of the X less than the specification, or plus the proportion of the readings that is greater than the specification. We draw the specification, not the data. The data is measuring the performance of the actual. The specifications are given from the designer of the product or the service. In this case, it is estimated to be plus or minus 0.5 microns of the center line or the average. The average is 1.5. The specification designed to be plus or minus 0.5. So when we add 0.5 to 1.5, that will be 2. So the upper specification will be 2. So in this part of the formula, we need to find the proportion of items that exceeding the upper specification. In this side, we are finding the proportion of the products or transactions that is less than the lower specification. And it was found from 1.5 minus the specification 0.5, which is 1. And to find the proportion, we go back to statistics. Phi multiplied with the mean for the specification minus the actual mean. Now, to see the difference between the actual and the specification, divided by the standard deviation estimate that we found earlier, plus 1 minus phi to get the both sides, because remember, in the normal distribution tables, this goes to the right side and this one goes to the left side of the bell shape. So that's why we need 1 minus phi, specification mean minus the actual mean divided by the standard deviation. That will lead us phi of minus 0.361 plus 1 minus 3 times 3.53. To find the value of the z-score in the table, we go to the z-table that we have covered on the statistics and look for those values. For this example, I have listed here the z-table for the to the left area of the normal distribution. So we will look for 3.6, 3.61, so 3.6 the z, and then we look for 3.61. It is 0.9985, and since this is for the left side, so we have to subtract that value from 1 in order to get 0.00015. So we subtract the value from 1 from 0.99985 to get the other side of the distribution in order to get the value on the right of the specification. On the other side, we will do the same. We will look for 3.53, 3.53, and it is equal to 0.9979. And in this case, we don't need to subtract it from 1. We use it as is because this is already on the left side of the distribution. Depend on the table you are using. This is covered in the statistics. If you are using two sides table or left side or right side of the table, this one minus here, this is from the formula, not from the table. So when you subtract them, you get the value 0.00035. This is the proportion of items that will fall beyond the specification limits. If you multiply this number with million, you will get 350 parts per million. They will be outside the specifications. If you convert that to sigma level, you can refer to the table that covered in the Six Sigma chapter. It will give you the estimate sigma level for this number of defects. So these considered to be defects will be exceeding the specification limit. This is very important to know and to conduct after you do your control chart to study your data or your process more. Further about the process capability, now we found the proportion that is falling outside the specification limits. There is also a process capability ratio. We refer to it as a CP or PCR. The CP PCR is the process capability ratio. This stands for the CP equal the upper specification minus the lower specification divided by 6 standard deviation. The standard deviation also found estimate from the previous formula, and the specification is already set by the designer to find this value, this is give you something different. This is a different interpretation about the capability of the process. That give you the number of non-confirming items. Here it shows you that whether the data or your distribution or your process, whether it is centered or shifted from the mean, and also it shows you the variability. To more understand about this ratio, I will show you this figure, which really make it easier to you. When you find the value of the ratio CP, if it is equal to 1, that means your data is centered. That means the natural tolerance comes in the natural process. It will be just on the specification. And in this case, any point will be a threat of exceeding the control the specification limits. However, if the CP is greater than 1, that means your natural tolerance or natural variation here, it is less than the specification, and that means it is better, because the natural variation could happen regularly, and in this case it will be away from the specification, so you will not exceed the specifications of the design by the natural variation. So as the CP is greater than 1, that means it is better. In the worst case, if the CP is less than 1, that means your natural variation is greater than the natural variation limit is greater than the specification limits. And in this case, you will be beyond the specification most of the time, okay? This is to interpret the ratio you found here. So what you can interpret about this value, 1.19, that means we have, you can tell that the process is capable as long the CP is equal or greater than 1, the process is capable. If it is greater than 1, that means it is capable, and the natural tolerance limit is less than the specification limits. So the variation of the natural variation will be less than the specification limits. To get it further, to see what is the percentage of specification you will use, you can calculate it from the formula, the percentage equal 1 divided by the CP that we just found times 100. When you get the value of the 84, around 84%, that means the process will use up 84% of the specification band, which is the area of the specification. So it will use 84% of the specification area. That was for the process capability. There are some importance also here in the control charts we have to mention about are those 3 points. The control limits are derived from the natural process, meaning that when you have readings, samples, then you do the calculations that we just did for the X bar R, for example, chart, then the control limits will be calculated. So it is based on your actual reading. The specification limits are from the designer. You don't get the specification from the data of the readings. You design the specification, for example, the battery lifetime, the car dimension, your product dimension, your product weight, your service transaction time, your leading time, your processing time, your time. You design them as a designer, as an engineer, okay, as a process owner. But the control limits come from the natural variation of the actual data. Always it is better to have the natural limits of the variation, which is the 3 standard deviation around the mean, to be less than the specification limits. And how to test whether this is happening in the actual, we had the CP ratio to test that and make sure if our natural limits is less than the specification or no. Otherwise, if it is greater, that means any natural variation will happen to the process, which is commonly be done or happen. it will exceed the specification. So your process is not capable to be performed and you have to redesign it. Your control limits, in the best case, if you have done your design very well and you run your process, when you gather the data, the ideal case to have the control limits are even less than the natural limits, which is also less than the specification limits. So any points exceed out of control, they will not exceed the specification limits. Those are very important. And here, lastly, there is no mathematical or statistical relationship between control limits and the specification. So there is no a relationship between them. That was from the designer, the control limits from the actual run data. That was all for the first part of control charts for variable for X bar R. We will continue with the more control charts of variables in the next lectures.